Welcome to the video Key Properties Toughness. Linear elastic finite element model calculates the state of stress beyond the crack tip for an ideal material. The state of stress is approximately identical for all ferrous materials depending on the elastic parameters. It defines the constraints to the plastic flow development. And this with reference to a CT, ASTM specimen, this control can be divided into two directions, the ligament direction and thickness of the specimen. The temperature and strain rate modify the material flow curve. The material model developed at University of Cassino on the Zanardi ADI 1050 megapascal ultimate tensile strength shows a good behavior at a low temperature and a high strain rate for this material. It is possible that this general behavior applies to the whole class of ADI materials thanks to the gamma FCC phase. Given the material-independent geometry and linear stress distribution, using the material-dependent uniaxial plastic flow, the plastic volume size depends on the material-dependent yielding surface, expressed through the equivalent stress. So if we adopt a Coulomb-Moore yielding surface expression, we see that varying the mu parameters, the material response varies. And if we think that to this yielding surface we can associate also the different necking behavior after the considered conditions, we can imagine that each material will have a different response on the plastic volume development beyond the crack tip. So this will distinguish the different material behavior when the condition of a plane strain is not guaranteed. And so with the state of a plane stress, we can have freedom for allowance of constraints in the material plastic volume. The plane strain small-scale yielding fracture toughness K1C is a material property measuring the resistance to the brittle transgranular crack propagation at the actual temperature. On this base, gold and glass can be compared between each other. The direct measurement of a K1C is possible following ASTM E399 on CT specimen of acceptable thickness, say for instance 45 millimeter in our case of ductile iron. But this direct measurement of K1C is possible only for fully pellitic ductile ions, that is average 30 megapascal square root of meter, and high strength conventional ADI, for example ADI 1200 megapascal ultimate tensile strength, which shows a K1C of about 81 megapascal per square root of a meter. But anyway, the K1C can never be larger than the given value that is given by this expression, square root of 0.045 multiplied by the Young modulus in gigapascal and multiplied by the yield RPO2 in megapascal. And this K1C is a maximum possible for a given material without at a condition of a no violation of the small scale yielding condition. And this is a problem when with ductile materials, and that where we are not able to measure directly the K1C property, and so we have to use the J approach. But the conversion from J to K is allowed only if the small scale yielding condition is guaranteed. And this is not always the case, even following existing measurements standards. And this makes a problem when you have to compare the fracture toughness of different materials, different ductile materials measured in different conditions with the different material standards. So if we get a measurement of a K1C that is made by a conversion of a J measurement, we can imagine that the difference between this K1C and the K1C given by the formula of the small scale yielding, that is the maximum possible K1C, can be said as a ductile shearing toughness that is added to the brittle fracture toughness K1C. In this slide, you see the actual values for ADI as in ISO 17804 that we can accept as valid K1C values. And they are compared with the line of the maximum K1C allowed with a small scale yielding condition. Values in ISO 1083 that was existing in 2004 and EN 1563 existing up to 2012 were cancelled, being very different between each other. In ISO 1083, valid ASTM E399 K1C were considered, also using low temperatures when the CT specimen was not sufficient to provide small-scale yielding. In EN 1563, 2012, a conversion from J measurement was adopted when it was not possible to obtain a valid ASTM E399 K1C with the possible violation of the small-scale yielding requirement. In this diagram, Sharpie V-notch trends for different Zanardi materials are converted into KJ1C following the Walling relationship. We did not investigate on the basic data and measuring procedures used for the correlation. The advantage of this diagram is on the estimate of the fracture toughness at the different temperatures. Thick lines represent room temperature, dotted lines -20 and -40 Celsius. The last two are coincident for ferritic perlitic ductile ions, so the red material. For IDI, LT, that is means low temperature and with a process with low silicon content, and IDI room temperature with normal silicon, and for two silicon solid solution strengthening ADI, only 1 point is given at each test temperature. The trend of silicon solid solution strengthened ADI seems aligned to normal ADIs, considering L25 Lynchburg 25 mm specimen instead of Y 50 mm thick used for the other tests. For ADI, ISO 17804 and ADI Walling show a parallel trend. ISO 17804 is more conservative than the ADI converted with the Walling equation, and this in turn is more conservative than the directly measured data. As from Walling approach, some ductile tearing toughness could be available only in the lowest ADI grades. In fact, a direct ASTM E399 K1C measurement was not possible using CT spacement up to a B thickness of 45 millimeters, side grooved, and with RPO2 799 megapascal, because of a too large ratio of P maximum divided by PQ that was larger than 1.10. ADI is low sensitive to strain rate. Then directly measured data and conversion from Sharpie V-notched can be done. Ferritic perlitic and low normal silicon ferritic rates show the same trend from the two data sources, being, again, EN more conservative. Discrepancies between the two sources exist for silicon solid solution strengthening, the so-called high silicon ductile ions. Following Walling, that is driven by the Sharpie V-notched, the dependence of K1C on silicon content and RPO2 is stronger. Probably it is an effect of the strain rate that needs to be distinguished from the static fracture toughness. The same approach needs to be adopted for IDI.